Okay, in this video we have four different antiderivatives to find. So let's start with A here. I have 2 cosine 4s ds. So I'm looking for a function whose antiderivative is this. Okay, and so I'm going to do it by substitution. I'm going to say let's let 4s be equal to some other variable. Let's call it x. Then that means that, so this implies that s would be equal to x over 4, and that implies that the rate of change of s, the differential of s, is equal to the differential of s with respect to x. I should say differential. I should say the differential of s is equal to the rate of change of s with respect to x times the differential of x. So ds is equal to, now ds dx is 1/4, because that's the derivative of this right here, dx. Now we're going to use this here. So we're going to say that this is 2 times the integral, because I can pull the 2 out. That's one of my rules. And so we're going to go cosine. Now 4s was equal to x, so we'll just plug in x here. And now ds, that's equal to 1/4 dx. And so now, if I go ahead and pull the 1/4 out, I get 1/2, because 2 times a fourth is a half. And this becomes cosine x dx. This guy right here, I know what its antiderivative is. So this will become 1/2 times, now the function, I need the function whose antiderivative is cosine x. And that function is going to be sine x plus c. Now the whole thing is being multiplied by a half, but 1/2 times c is still just c, because it's just a constant. And so this gives me 1/2 sine. Now x was equal to 4s. So we'll plug that in there. So now what we have is our function as a function of s. So f as a function of s is equal to this. And if we go ahead and we were to differentiate that, we'd end up right back at the beginning. Okay, so 1/2 sine 4s plus some constant of integration is equal to the antiderivative. Let's do part B now. So for B, we've got the integral of 1 plus the secant squared of theta d theta. So what I'm going to look for is 1 plus secant squared d theta, is that a derivative, okay, of any of the trig functions? And it doesn't look like it is. So the next thing I'm going to look for is it possible that this right here is one of my Pythagorean identities? So I'm going to go back and I'm going to look at my trig identities, or I'm going to think about splitting this guy up. Okay, so if we looked at our trig identities, we might find one that's got this in there. Okay, or if we split it, what I mean by split is to write the integral like this. But when we split, we have to make sure that we know how to go backward from 1, which isn't that hard to do. And then we need to know if secant squared is the derivative of anything. And it is. It's the derivative of tangent. So we'll go ahead and we're going to use that right here. So let's do each of these separately. So this first one says we're looking for a function whose derivative is 1. So, and it's got to be a function in terms of theta. And so that function, call it f, in terms of theta, is just theta plus c. If you differentiate this with respect to theta, the derivative, think about this as like an x. The derivative of x, well, it's just 1. So the derivative of theta is just 1 plus 0, so it's just 1. So this guy right here is our antiderivative for this. Okay, so we've got that. So f of theta, which is this. Now we need to get the antiderivative of this guy right here. And so what we'll do is we'll we'll look back and we'll say that the derivative of tangent, so let me call this guy g. Okay, so if we work in reverse, let's call this guy c1 and this guy c2, so they're different. It's really irrelevant. But I've got these two guys. Now if you differentiate this guy right here, you end up back at secant squared. So I just need to add these two functions together. So this is a function, this is a function, which means I can add these parts together. So I get the following. I get from the overall derivative, we'll call it h, the overall antiderivative is going to be equal to tangent of theta plus some constant c, where c is equal to c1 plus c2. And so that gets us our antiderivative. Okay, let's work on c now. So c is the tangent of 2x times the secant of 2x dx. So if you look back at your derivatives, the derivative of just secant x, that's equal to secant x times tangent x, just like that. Well, I see tangent x and secant x in here, so its antiderivative is going to lead us back to here. The problem with this, though, is it's not just x, it's 2x inside. So to make it look like this over here, we're going to make a substitution. So let's go ahead and call this some other variable. Like let's say we call it theta. So we'll say let theta be a function of x and let theta be equal to 2x. Well, this implies that x is equal to theta over 2 if we want it that way. And that implies that dx is equal to 1/2 d theta. This right here, so I'm using my differentials. This right here is d theta. Dx d theta. Like that. So remember, dx is equal to dx d theta times d theta. So we'll make this substitution in here. Now what I'm going to do over here is I'm going to say this is the tangent of theta. This is the secant of theta. And dx has to be replaced, and dx is 1/2 d theta. Like that. Now I have the same variable floating around here, so we're good. We can't just leave this guy as a dx. So let's pull the half out. And then we get the following. And the antiderivative of this with respect to theta is secant. So this leads us back to 1/2 secant theta plus the constant of integration. And of course, theta was 2x. So this is 1/2 times the secant of 2x plus c. And when we multiply 1/2 in here, that's still just the secant of 2x plus c. Now, if you feel more comfortable, you can call this guy c1, and then we can say c is equal to 1/2 c1, and then there's your replacement. Okay, this ends up giving us our antiderivative. Okay, now we got one more here. So let's go ahead and try d. So d says we need to integrate the sine of x plus the square root of x dx. So what I'm going to do is I'm going to use, I'm going to think about distributing, because I'm going to use the sum formula here in anti-differentiation. So this is going to be the integral of the sine x dx plus the integral of the square root of x dx, just like that. So let's work on this guy over here first. Do we know a function whose derivative is sine? Well, yeah, we do. That's negative cosine. So this right here is this guy. Now we're going to add to it. We need the derivative here. So what we do is we need a function whose derivative is square root of x. Well, let's think about that. Okay, we can do, we can go ahead and play around with this guy if we want to, but I think the easiest way to look at this is we have x to the 1/2. So again, to go backward, we worked on those rules. We add 1 to the power, and then we divide by that guy. Okay, and of course we're going to add a constant of integration here at the end. So this will be x to the 3/2 over 3/2, which is x to the 3/2 times 2/3. So of course we're going to add that constant of integration, put it right here. And so this is going to be 2x to the 3/2 over 3 plus, and let's call this guy c2. So constant number 2. So this ends up being 2x to the 3/2 over 3 plus c2. And now if we let c1 plus c2 just be equal to some other variable, we'll call it c, then our antiderivative as a function of x is equal to 2x to the 3/2 over 3 minus the cosine of x plus the constant of integration. So I wrote this guy in the back because it was negative, but you can do it any way you want. But this guy right here comes from this right here. Okay, so again, we have to play around with these guys, and we're always looking for how do we go backward. What was the guy whose derivative is this integrand?